Jorge Nocedal 侯黑诺塞达尔，美国西北大学教授，美国国家工程院院士，美国工业和应用数学学会会士。长期以来，他致力于解决非线性优化的问题，特别是图像、语音识别、推荐系统和搜索引擎中的优化问题。公开发表学术论文100余篇，还曾担任美国工业和应用数学学会优化期刊主编和美国工业和应用数学会评论副主编。因在非线性优化方面的杰出成果，他被授予冯诺依曼理论奖等众多奖项。他是应用数学与计算机科学领域的领军人物。
Hey, let's welcome Professor Nocedal, and he is going to talk today about optimizations of a function whose derivatives are not necessarily available, and especially in applications such as adversary training and reinforcement learning cases. And so let's welcome Professor Nocedal. If you're ready, could you share your screen?
All right, very good, thank you.
This is great. So let's put on the play mode.
Well, thank you very much for the invitation. Hi to everybody who is there. I have no idea who is there, but I'm very happy to speak to you about optimization. So this talk is going to be just about that subject. I think optimization is one of the pillars of machine learning. And instead of giving you a broad overview of work in optimization, I'm going to focus on just one problem, and that is the black box optimization problem that Subin was mentioning a while ago. And before I start, I should give credit to my collaborators. The work that I will describe here is based on 2 papers that have appeared already in SciM Optimization and a forthcoming paper. All right, so let me start with just some general comments at the very beginning. Deep neural networks have been so successful. Now, why did this happen? It was clear that there was vision there, but in this particular case, there was luck. And I want to explain what I mean by this. Well, the great vision was that there was an intuition, goes back to, I don't know, many decades, that a certain structure of a prediction function would be very useful for for generating representations. So in particular, there was this intuition that a composition of functions, as in a feed-forward neural network, would have the capacity of making interesting predictions that turn out to be very successful first in perceptual tasks, as you know. Well, the second observation that people made much later on is that these structures could be trained, that there was a concept called backpropagation that could help you identify among the class of all functions of this form, one that would have a very good prediction capability. So the intuition of the structure of the prediction function, plus the fact that it was backpropagation, was going to make this field possible. Now, backpropagation means really 2 things. In the beginning, people used to put them together. Backpropagation means the ability to compute the derivative of the loss function with respect to all the parameters, and then the possibility of feeding that derivative information to a gradient-based method and asking it to find out a minimizer of the loss function. So the backpropagation then is, to me, just the chain rule for differentiation. And then on top of that, you can apply a gradient method. And if you run your gradient method long enough, it's going to give you good values of the parameters. Now, why is it that there was luck? Well, it turns out that the optimization problem that arises in deep neural networks is non-convex and stochastic problem. But the key word here is non-convex, which means that we do not know how many minimizer does it have, nor do we know that if we run an optimization process, it will actually give us an acceptable solution. So here on the right-hand side, I have a picture of a non-convex function. And if you start the optimization from two different places, you end up with two different solutions. So it turns out that the field of deep neural networks, and I'm not talking here about a one-layer neural network, because that's simpler. Deep neural networks, which are highly non-convex, are relying completely on the ability of optimization algorithms to identify a good minimizer of the loss function that you have, and on giving you robustness and stability. Now, from the very beginning, people noticed that maybe there could be a real problem with optimization, that things might not work out the way they did. So in 1961, Minsky, that as you know, wrote a paper critical of the perceptron, wrote, "I doubt that any one simple mechanism, such as hill climbing, that means the gradient descent method, we will find a means to build an efficient general problem-solving machine. I do not believe that we're going to have a problem-solving machine that is based on a gradient descent method." That's what he's saying. And later, in his book with Papert, he says, if we can detect relative improvement, meaning if we can compute derivatives, then hill climbing, in other words, gradient methods, may be feasible. But its use requires some structural knowledge of the search space. And unless this structure meets certain conditions, hill climbing may do more harm than good. So he's just expressing what I had in the picture before. If you don't understand the non-convex optimization problem and you just rely on running the gradient method, how do you know you will be getting consistent results? Well, he says, unless we know some structural knowledge. I don't know exactly what he meant, but it turns out that deep neural networks, even though they're complex, they do have a benign structure. We know that, but in what way is this structure benign is one that we do not fully understand. People know about invariances, topological properties. They're being investigated, and they're nice answers for simplified models, for very wide one-layer neural networks, or for other models, but never for those models that are being used in practice. So we don't completely understand why the optimization is working and whether we have guarantees that it will always work. So is that the case in general in machine learning, meaning that optimization just works? Well, remember that prior to neural networks, most models that were being used gave rise to convex optimization problems. And then it was possible to come up with guarantees about the optimization. In neural networks, things are working out for reasons we don't understand. But if you take some other topic like reinforcement learning, well, you will no longer have this luck. People will find that there's local minima and that the optimization process is not clean and it's at present is not well understood. So why do I mention this? Well, first of all, to emphasize the crucial role that optimization is playing in the design of the architectures. For example, my understanding from Kai-Ming He is that the motivation for developing a residual neural network was to find one that was easily optimized, or one that answered the question of why is it so difficult to train the identity function? So here optimization is having some influence or inspiration in the architecture of a neural network. But maybe a bigger warning sign is the following. Some of you may have heard that people want to use neural networks, deep neural networks, to solve partial differential equations, or maybe inverse problems. Let's assume that this is possible, that someone comes up with an architecture that is able to solve a particular partial differential equation. Now, do we know that if we change the data, the optimization will still work? This question really has to be answered because it is not clear that any architecture that you have, which is a composition of functions, there may be convolutions or there may be something else, is one where the stochastic gradient method is going to give you consistently the same function values. So this is where we are. I think that the pioneers of the field could not have foreseen that optimization was going to work the way it is working today. And we either need to understand the optimization process better or create architectures that are amenable to an understanding, so that we know that one of the pillars of the field is reliable. All right, so that was just a general comment, not really related directly to my talk. And I would appreciate any comments that people have about that subject. All right, so let me move on to the problem that Zubin actually touched on when he was talking about Bayesian optimization. Suppose we wish to minimize a nonlinear function, and suppose, just to make it simple, that the function is smooth, differentiable, and not necessarily convex. But we have a nice function we want to minimize, but every time we evaluate the function, we are not able to obtain its gradient. So unlike the loss functions that occur in some applications of machine learning, we can have a concept as occurs in reinforcement learning, where it's very difficult to compute a gradient of good quality. So we are only able to observe the function, but every time we observe the function, we observe it with noise. And so the question is there an algorithm that can solve an optimization problem that is derivative-free and with noise when the number of variables is in the thousands? Can we do that? And this is the question that motivated some of the work that we started about 4 years ago, because to my knowledge, the answer was no at the time. And so we went ahead and we developed a method that we published, and it is based on the idea that in order to do optimization of noisy black box functions, perhaps the best avenue is to make approximations of the gradients and then build quadratic models based on them. Around the same time, Nesterov and Spokojny wrote a very impressive theoretical paper. They had to do also with zero-order optimization, with derivative-free optimization. And what they did, I will explain it later on. But at the same time, then we came up to that conclusion of looking at approximation of derivatives. So let me state the problem a little bit more formally here. The function that we would like to minimize is phi of x. It's a nice function, but we cannot observe it. Every time we want to evaluate it at a point x, we obtain really the function f, which is the true function plus some error. And every time you want to compute an approximation to the gradient of that nice function, we have an error or two. So we observe f and g. The question is, can we minimize f as well as possible while observing only f, the contaminated function, and using gradients that are also contaminated, g? So a typical case here is where you have a black box simulation. The unknowns are x. You feed x in there, and you get the objective function value. Now, I want you to think a little bit more broadly than machine learning, because derivative-free optimization arises in so many applications. And sometimes one learns more by going into another field and contrasting it to what we know in the area that we are interested in. So in this particular case, I'm going to step back and say, well, where else do I know that we need to minimize black box objective functions with noise? And it turns out that one very important application has to do with what we call computational noise. And that refers to the fact that sometimes we have a computer program here in black that evaluates some function, and the evaluation of the function may require the solution of a differential equation, say. And that differential equation requires an adaptive method, uses an adaptive method for generating a grid. And so if we evaluate this function twice at exactly the same parameters, we have the same solution. But if we change the value of x a little bit, the mesh that we use to compute the function value may change. And so the function value could have a jump, as is shown here in the graph on the right-hand side. Now, many of you are familiar with iterative methods of solving linear systems of equations. So another example that is good to think about is, suppose that we evaluate a function, and in the process of evaluating the function, we have to solve a linear system of equations, ax equals b. But that linear system cannot be solved exactly and may be very big. And so we use an iterative method, like the conjugate gradient method, to solve that linear system, and that gives us the objective function. If I do this twice from the same point, I get the same answer. So the error is not stochastic, it's deterministic. But what happens if I evaluate the function at a very near point, xk, and now the iterative method for solving the linear system, instead of using, say, 8 iterations of conjugate gradient, uses 9 iterations of conjugate gradient. It means that the linear system that had to be solved here is solved more precisely. So you get a more precise value of the objective function. And so once again, we have an objective function. We'll have these tiny, very small bumps. Now, they may be small or big, but they're all these bumps. Round-off errors will create this, and low-precision arithmetic will do that too. All right, so that's one case. The other case is where you have stochastic noise, and that's the one you're most familiar with. Stochastic noise or deterministic noise. So here is an example of where you might want to use derivative-free optimization. This is perhaps a little bit of an academic example, but we want to do adversarial training. There is a neural network that we're observing. We can see the input and the output, but we're not the owners of the neural network. We cannot do back propagation in order to find a sensitivity analysis, in order to find out how to most easily change the results. So what we could do is formulate the following problem. Someone is going to feed an image here that corresponds to class C. I want to find an image that is slightly perturbed that will be assigned to a very different class by this neural network. So I want to play that adversarial example just by changing the image. How is this formulated as a derivative-free optimization problem? Well, the given image, let's suppose that the given image is x0. I want to find another image that is as close as possible to that original image. And I want to make sure that I misclassify that image. So I choose a class T, which is an incorrect class, and I would like the image that is close to x0 to be as close as possible to class C. So I'm going to penalize not being there, and I have this objective function, and the values of x vary between 0 and 1, and I do not know how to compute the derivatives of this model because I do not have access to the neural network. Well, there are various formulations of this, but this is just an example of something we could do. Now, of more current importance is policy optimization and reinforcement learning. Okay, this problem now is going to be a clearly stochastic optimization problem with stochastic noise. We want to find a policy for controlling a dynamical system that maximizes a cumulative reward that you've set up on given tasks. For instance, a robot has to do some tasks. We want to find a policy, but we don't have a physical model of the system. And so the problem ends up being formulated in this manner. We want to find the expected reward that depends on some parameters W, and it's a stochastic function that depends on a random variable xi. Now, the stochasticity and this expectation is taken to randomness that are due to several sources. Perhaps the initial point in the choice of your policy, the fact that whenever we evaluate this function, we do a sample approximation to that, running only a mini batch of episodes and not the correct objective function. So we will have some noisy objective here, given how well we approximated the function, or the randomness can come to the fact by the fact that the environment is stochastic. Any simulation has uncertainty there. So here is a problem for which there is such thing as a policy gradient, but there are arguments for trying to tackle this without trying to compute that policy gradient. Because the policy gradient may be have too much variance. All right, so these are some examples of when we would like to do derivative-free optimization. So let's now slow down here. Everybody can think about optimization. It's so central that everybody has their ideas about how to create algorithms. How do you perform derivative-free optimization? You can only observe function values. Well, we can go to a textbook on complexity theory, for instance, Nesterov, and it will not be very helpful what we find there. It will say that if you do random search on a grid, in other words, evaluate the function on a grid many times and choose the best value and see if you're satisfied and repeat the process, this will have as good complexity on difficult problems as more intelligent algorithms. But we know that evaluating a function on an n-dimensional grid is not scalable. It's impractical. That's not a good algorithm. Complexity theory does not help us there. Well, it turns out that the numerical analysis community has developed lots of algorithms for zero-order optimization. The Nelder-Mead simplex method, pattern search methods, direct search methods, evolutionary methods that are useful for discrete problems, but they're not scalable. None of these methods are scalable. And evolutionary methods are not appropriate when the variables are continuous, because they're going to be better methods to do that. So it turns out that for a really long time, the optimization community and many practitioners relied on methods that are actually not good at all. The methods that I just mentioned were shown by Moret and Wild. In a very beautiful study, they showed that all these methods that are used by the thousands are really inferior to a method that learns from function values that have been observed and creates a model as you go along. So this method that I will talk about now by Moret and Wild does the following. Suppose that you have evaluated the function at 4 points. Well, maybe a natural idea is to say, don't forget about that information that you have. Use those points, enough of them, to create a quadratic model of the objective function. And then just find the minimum of this model, move to that point, and repeat the process. So the way these model-based methods work then is you create a quadratic model and you minimize it. Now you minimize it subject to a trust region. You don't want to move too far because in fact, if you have function values and interpolate them, you may not get a convex function. Especially if there is noise, you may get a concave function that will not have a minimizer. So you want to make sure that you obtain the minimizer of this model on a region where you can trust the model. Now, how many parameters do we have to determine in a quadratic model? Well, we need a whole Hessian matrix and we need a gradient. And that is this amount of information, about d squared piece of information we need in order to determine a quadratic model. And that's a lot. D squared pieces of information is going to require of the order of d squared function values in order to interpolate and create such a model. But fortunately, Powell had a very brilliant idea and said, well, in fact, we don't have to base a model completely on interpolation. Suppose that I define the model of the Hessian of my model such that the new model interpolates the functions that I have here, and that the Hessian matrix that I have is as close as possible to the previous Hessian I had. So by absorbing degrees of freedom in this manner, I was able to reduce the amount of information that we need from the amount of information that we need from d squared to OD. And this method, although it has high arithmetic cost, delta to the, d to the 4 or d to the cube, was considered until very recently to be the state-of-the-art, one of the best methods that there is for derivative-free optimization. And the method is completely described in the book of Kohn, Scheinberg, and Vicente. And as I mentioned, this was considered the state-of-the-art until very recently. Okay, so we have a critique about this method. I used to think that this was really the way to go. But by constructing quadratic models, we're not putting particular emphasis in getting a good gradient estimate. We just want to show that the quadratic that we're creating approximates the function globally in the trust region. Second, the method depends always on having a trust region. And if the trust region is too small, the steps will be too short. If the trust region is too large, you will end up rejecting steps. And the trust region is not a scale invariant concept. It's something difficult to handle. A third disadvantage of these methods is that they're not parallelizable. So you keep evaluating one function value, updating your model, and it does one function value at a time. So we thought that there should be an alternative. And in that SciOp paper that I mentioned of 2018, by the title there in green, we came up with the following strategy. It seems to us that in order to create a good method for zero-order optimization, we should place as much effort as possible in approximating the gradients. And then don't worry about the construction of the quadratic model. Delegate that construction to quasi-Newton methods that have known to be remarkably effective. And there's a method called the Bfgs method that is widely used in all of engineering and not very much used in machine learning, but very much used because it only uses first-order information, but can give you a superlinear rate of convergence. So we thought about doing that. Approximate the gradients well, delegate the construction of the quadratic model to quasi-Newton updating, and use a third ingredient. And that was an idea that Hamming, the famous Hamming computer scientist of Hamming distance and Hamming coding, proposed quite a few years ago. And we're going to use it in order to make sure that our gradient approximations are correct. Now, we're going to minimize a noisy function. There's a noisy function in red. And what I claim we're going to do is we're going to approximate the derivative of that function. What is the meaning of the derivative of a noisy function? Well, here is one possibility. Nesterov, I mentioned in his paper with Spokojny, said, well, if you have a noisy function, what you can do is you can smooth it. So f delta here, the expected value of f plus small displacements along random Gaussian directions u, average them all out, takes the expectation of all these values, will create in the neighborhood of the solution a smooth approximation to the function, and then compute the gradient of that smoothed function. So that's the meaning of the gradient of a noisy function, the gradient of the smoothed approximation. And together with that idea, then they propose a method that simply computes the gradient of the smoothed function and moves along the negative direction a certain step length. And Nesterov and Spokojny prove some very impressive complexity results that include problems that are non-smooth, problems that are Lipschitz continuous, and all sorts of classes. They have a very rich complexity theory for algorithms of this form. Now, the formula for computing the gradient of the smoothed function looks simply like a finite difference. So how do we exactly compute the gradient? You're at the point x, you choose a random Gaussian vector u, move a distance d, take the finite difference approximation and multiply it by the direction u that you found. Now, this could be done only once, or you could take the average of m of these random vectors. And so it's like computing directional derivatives and updating them. This is how you're going to get derivatives. And we're going to see that this is interesting. This method actually works well for certain classes of problems in machine learning and may not be the best for other applications in science. Well, the other thing we can do, of course, is just go and do classical finite differences, which is really a special case. Finite differences moves along the coordinate directions. And the key question, if you have a noisy function, is how to choose the differencing interval. Now, this is where we're going to go back to the work of Moret and Wild. If we can estimate the noise level of a function, we claim that we can compute a good finite difference interval to use with classical finite differences. And we will be able to obtain almost optimal, nearly optimal estimates of the derivative. Just to reiterate, suppose that we know what is the noise level that is contained in your function. Then, for forward differences, take a differencing interval, which is the square root of that noise level. And for central differences, it's going to be the cubic root, where this happens to be a constant, the second derivative. But it's pretty much just take the square root of that function and do finite differences that way. Now, to try to convince you that it makes sense to compute derivatives of noisy functions, I have two pictures here. And now this is a more reasonable function than the one I showed you before. Here's a nice smooth function, and we've added uniform noise to it with standard deviation 0.25. And we go to our formulas, and we see what happens if we choose the finite differencing interval to be too short. For instance, if you try to observe these two function values, the slope of the function does not really match the true slope of the true function. However, if you space the points well enough, age correct is 0.28, if you evaluate the function at points that are sufficiently well spaced, then you're going to get derivatives that are good approximations to what you have. So the question then is, how do we obtain the noise level of a function? And how do I do it in such a way that will work both for deterministic and for stochastic problems? And this is where the idea of Hamming comes in. To estimate the noise of a function, phi, the noise is epsilon, and suppose that the standard deviation is sigma, what you can do is choose a random direction. Just at x, where you want to compute a derivative, choose a random direction and evaluate the function at q plus 1 equally spaced points from there. Suppose that you evaluate it at 6 points, 7 points, along one particular direction. And then do the following. Okay, so you've computed now the function value at 7 points along a line. Then here comes the Hamming table. Here is a value of this function whose derivative we want to compute. And we've added uniform noise of magnitude 10 to the minus 3. We're going to have 6 additional points, a total of 7. And what we do is the following. Evaluate the function at all those 7 points. Here it is. And then take the difference in these function values. This difference here, that difference here, and so on. So these are the differences of these function values. Then take the differences of those differences. This minus that and put it here, this minus that and put it here, and so on. So you keep producing a table that will have shorter and shorter columns because of the way we're taking differences of differences. But now, what do we know about this? We know that, for instance, the first difference is an approximation to the derivative with an error of, if I divide by h, this will be an approximation to the derivative. But in general, this quantity should be of order h. if I'm approximating just to first derivative. Now for the kth case, for the kth difference is going to be h to the k. In any case, what I'm saying is, if you did not have noise here, and you computed these columns, these differences, these quantities would be converging to zero very rapidly. H squared, h cubed, h to the fourth. But if you have noise, what you're going to be doing when you take higher differences, you're going to be differentiating the noise. And so the noise is going to appear in this Hamming table. And the way we obtain it is by taking averages of these quantities. So we take the differences, take averages of what we see in the columns here, weighted averages, and report the numbers. And when these numbers do not change anymore, we see that all what we're doing is we're obtaining noise. And we've extracted the noise level of the function automatically. And this procedure will work if you have stochastic noise, which you could have obtained by sampling at the same point. But it will work also if you have deterministic noise, where sampling at the same point will not work because the function at the same point will give you always the same function value. So using this Hamming table, we can feed it into the algorithm. This is the theory behind it, and find out how to choose the differencing intervals for those two functions. Yes. Okay, very good. All right, so now having chosen this, I can now come and propose the method that we have been promoting. Once you have gradients, why keep doing just first order methods like Nesterov does? Why not use a quasi-Newton approximation based on differences in gradients and develop a method in that way? And here is a slide that presents our final method, right? So, to summarize, to minimize a function without derivatives, first estimate the noise, compute a finite difference interval, compute a gradient approximation, use difference in gradients to compute a quasi-Newton direction, take a step, do a line search, perhaps, if necessary, recalculate the noise, and we're able to establish convergence results for this algorithm that we have proposed here. And we hope that this type of method that uses second order inspires people to go beyond using first order methods for zero order optimization. All right, so it looks like I'm out of time, so I will stop here for questions, right?
Well, thank you very much, Professor Nocedal. This is a very interesting work. I actually have one question, and that is, have you applied this new approach into any reinforcement learning kind of applications?
Yes, we have. We have applied this approach, and we've also applied Nesterov's approach for solving the Mujoko problems. And I'm going to leave those slides there with you, because in the slides that I could not report, we have results there for problems in the Mujoko collection. And we found some interesting results.
Great. Also, follow up on that is, how often do you see this reinforcement learning or learning and probabilistic learning? It can reformulate it as optimization issue, optimization problems, and then solve them with approaches like what you just proposed or other approaches.
Well, in reinforcement learning, what you want to do is maximize a reward function. This is the way you phrase the problem. And right. They're always stochastic. And there are two ways to do that. You can do what is called the policy gradient method, or you can do derivative-free optimization. But if you can imagine, you have a robot and you want to train it to do an activity. This is a system that is difficult. It's going to be noisy. And it's going to be very difficult to compute derivatives exactly. So the derivative-free setting is natural in that case.
Oh, sounds great. And I guess those are the two questions that we have. And thank you again for the wonderful and also insightful talk. And well, thank you for sharing with us the slides as well. And otherwise, okay, thank you for coming to our conference. And well, you stay healthy and stay well.
Thanks very much to meet you. It's a pleasure.
Great.
You too. Bye.
Bye bye. 好，各位同学，各位来宾，我们今天上午的大会到此结束，谢谢大家。